fully formed galaxies, 100 billion solar masses, existing just 400 million years after the Big Bang. Webb found them, and according to every growth model, they should not be there. But it is one of 10 discoveries now forcing scientists to rewrite their models of the cosmos, from unexplained rogue planet pairs drifting through Orion to a Hubble constant that refuses to converge. In October 2023, the James Webb Space Telescope completed the first epoch of its Jumbo survey, targeting star-forming regions like Orion and Carina with deep NIRCam imaging. What surfaced from the data was unexpected. Dozens of wide binary pairs, each composed of objects with masses between 1 and 4 times the mass of Jupiter, drifting together across gaps as wide as 900 astronomical units. These are not planets orbiting a sun, but free-floating planetary mass objects bound only to each other. By March 2024, the confirmed tally stood at around 80 such pairs, each system meticulously verified through multi-epoch astrometry and color magnitude fitting against the ATMO 2023 evolutionary models. The median separation, about 350 astronomical units, stretches far beyond what standard fragmentation theory allows for objects this light. Classical models set a lower mass limit, around 7 Jupiter masses, for fragments that can condense out of molecular clouds, citing the so-called opacity limit. Yet the jumbo pairs fall well below this threshold, and their survival at such wide separations contradicts the expectation that only stars or brown dwarfs can form stable binaries on these scales. The proper motion coherence, measured over a year, rules out chance alignments, confirming these are true gravitational pairs. For theorists, the implication is clear. The physics of fragmentation and the initial mass function must be revised to account for a population of planetary mass binaries forming directly from cloud collapse, not as ejected remnants. The discovery of jumbos forces a re-evaluation of how efficiently matter fragments at the smallest scales, opening the door to even more exotic possibilities for planet formation in the galaxy. The Cartwheel galaxy's outer ring, shaped by a head-on collision, offers a rare glimpse into accelerated star formation. As a shockwave sweeps outward, gas compresses and ignites a burst of new stars along the expanding arc. Data from the MIRI instrument on the James Webb Space Telescope revealed that the ring's 7.7 to 11.3 micron polycyclic aromatic hydrocarbon ratio signals a radiation field much stronger than in typical spiral arms. Star formation surface density here tops 1 solar mass per year per square kiloparsec, 10 times the galactic average. Dr. Lianhua Qi, who models these dynamics, finds the Cartwheel's ring turns gas into stars with striking efficiency, compressing tens of millions of years of activity into a single sweeping front. Inside dense molecular clouds, Dr. Sofia Alvarez tracks Class 0 and Class 1 protostars in clusters younger than 100 million years. Surveys now show collapse from cloud to protostar can finish in just 300,000 years, half the expected time. This rapid, decisive collapse, seen in the scarcity of young protostars, reshapes our sense of how quickly cosmic structures transform gas into stars. Dr. Rina Matsumoto, a substellar population analyst, began comparing the Jumbo survey results with previous brown dwarf censuses. Using the James Webb Space Telescope NIR-SPEC gravity diagnostics, her team cataloged objects straddling the deuterium burning limit, about 13 Jupiter masses, and found a pronounced over-representation of bodies just below that threshold. The local census revealed that for every brown dwarf, there were nearly 2 planetary mass objects occupying the so-called substellar tail, far more than canonical models predicted. The mass function, when plotted, showed a continuous rise toward lower masses instead of the expected decline, suggesting that the initial mass function, IMF, may not be universal after all. In Orion and Carina, the frequency of these low-mass objects exceeded the predictions by a factor of 3, hinting at a breakdown in the standard fragmentation paradigm. Dr. Matsumoto's analysis closed the case for local star-forming regions. The substellar population is not a smooth extension of the brown dwarf sequence, but a distinct, elevated tail that compels theorists to question whether the IMF low-mass end can be generalized across the galaxy. Dr. Marcel Dubois, a gravitational lens modeler, began reconstructing mass maps for galaxy clusters using JWST's ultra-deep N, IRCam, and NIRISS imaging. The data revealed a pattern that standard cold dark matter models struggle to explain: dozens of small-scale mass perturbers, each with masses between 100 million and 1 billion solar masses, scattered throughout the cluster cores. In clusters like SMACS 0723 and El Gordo, her team identified more than 30 such sub-halos within a 150 kiloparsec radius, all required to match the positions and shapes of multiply-imaged background galaxies. These substructures are far more numerous than predicted by collisionless cold dark matter simulations, which typically forecast a steep drop-off in sub-halo abundance below 1 billion solar masses. The lensing models, anchored by more than 150 spectroscopically confirmed arcs, leave little room for error. The gravitational fingerprints of these sub-halos are imprinted in the distorted images themselves. This overabundance at small scales is not a subtle statistical excess, but a robust feature that persists across multiple clusters and independent lens reconstructions. The implication is direct: either dark matter is not as collisionless as previously thought, or the small-scale power spectrum contains more structure than the canonical model allows. As mass maps grow sharper with each new JWST cycle, the tension between observed substructure and theoretical predictions continues to widen, forcing cosmologists to reconsider the microphysics of dark matter itself. On September 17, 2023, the James Webb Space Telescope's NIR SPEC instrument recorded 2 full transits of K2 b, a sub-Neptune planet orbiting an M-dwarf 120 light-years away. The spectra revealed a striking mix: carbon dioxide at nearly 1% and methane at about 0.2%, both measured with 30% uncertainty. Dr. Niku Madhusudan, leading the atmospheric survey, noted these levels challenge expectations. At K2 18b's temperature, models predict either methane or carbon dioxide should dominate, not both. Yet both gases appear together, signaling chemical disequilibrium, likely driven by vertical mixing or photochemistry. The mean molecular weight of 2.9 grams per mole points to a metallicity 12 to 30 times higher than the Sun, far above what is typical for sub-Neptunes. A muted water signature, paired with strong methane and carbon dioxide, hints at a high-altitude haze or cloud deck shaping the spectrum. These findings force a rethink of how temperate exoplanets process heavy elements, making K2 b's atmosphere a new benchmark for studying volatile rich worlds. WASP-39b, a gas giant orbiting a star 700 light-years away, has become a proving ground for atmospheric chemistry in extreme environments. When the James Webb Space Telescope's NIR SPEC and NIRCam instruments returned their first spectra, the data did not just confirm the presence of water vapor and carbon dioxide. They exposed a pattern that standard equilibrium models could not explain. Abundances of sulfur dioxide and other photochemical byproducts appeared far higher than predicted, while methane was unexpectedly scarce. The radical mismatch between observed and modeled species pointed to active photochemistry, ultraviolet-driven reactions breaking down molecules and creating new ones at rates that defy the assumptions built into earlier models. Dr. Priya Sethi, a photochemist specializing in exoplanet atmospheres, led a team that applied multi-band retrieval fits to the WASP-39b data. Their analysis revealed that key reaction networks were missing crucial pathways for sulfur and oxygen radicals, and that vertical mixing must be far more vigorous than previously thought. The result was that existing models built on equilibrium chemistry failed to reproduce the observed spectrum across multiple bands. To match the data, researchers had to expand their reaction networks, incorporating dozens of new photochemical reactions and accounting for the interplay between high-altitude ultraviolet flux and deep atmospheric transport. WASP-39b's spectrum now stands as compelling evidence that exoplanet atmospheres are shaped by complex non-equilibrium chemistry, forcing theorists to rethink how planetary envelopes evolve under the glare of their parent stars. Lyman alpha damping in the James Webb Space Telescope spectra has revealed a universe far less uniform than classic reionization models anticipated. Instead of a smooth global transition from neutral to ionized hydrogen, the intergalactic medium appears patchy, with vast regions remaining opaque to ultraviolet light even as neighboring zones clear. Dr. Jean-Michel Roux, a cosmological modeler, mapped these spatial variations using hundreds of high redshift galaxy sightlines. His analysis found the neutral fraction at redshift 7 ranged from nearly 0 in some volumes to over 50% in others, a variance too large for models that predict a gentle, synchronized reionization. The data suggests that reionization advanced in fits and starts, shaped by local galaxy clustering and feedback, not by a universal timeline. This patchwork pattern challenges the idea that the early universe's evolution can be captured by a single, averaged curve, forcing theorists to rethink how ionizing photons carve through cosmic structure. A new round of Cepheid observations with JWST has put the Hubble constant debate under a sharper lens. Using the telescope's infrared sensitivity, astronomers recalibrated the Cepheid-based distance ladder, minimizing dust effects and zero-point uncertainties that clouded earlier measurements. The result is a local Hubble constant of about 73 kilometers per second per megaparsec, with an error margin of just 1 kilometer per second per megaparsec. This value stands in clear contrast to the 67.4 kilometers per second per megaparsec predicted by Planck's CMB analysis. Even after accounting for systematic errors, the gap remains. The JIWST data confirm that the local universe is expanding faster than early universe models predict, keeping the so-called Hubble tension alive and unresolved. Galaxies with stellar masses between 10 billion and 100 billion suns are now confirmed less than 500 million years after the Big Bang. Age fits from the James Webb Space Telescope's NIR spec data place some at over 200 million years old, implying star formation began almost immediately after the first light. Theorist Dr. Julian Becker, convener of the 2024 Cosmology Models Workshop, recalculated growth curves and found these galaxies outpace every lambda CDM prediction by orders of magnitude. The most massive, JADES GS 13.0 at redshift 13.2 forces models to allow for star formation efficiencies and halo assembly rates far beyond what simulations considered possible. Each new data release deepens the mismatch, leaving cosmologists to question whether the fundamental physics of galaxy formation needs rewriting. Astrophysics is now forced to confront a universe more intricate than models predicted. Each Webb revelation exposes gaps in our understanding, demanding new theories in real time. What we thought was settled is unsettled. In science, certainty is provisional, and discovery, not doctrine, drives the frontier forward.